So in the last couple of videos, we talked about distance, displacement, speed, velocity, and acceleration. And in this video, we're going to try and derive some important formulas that relate them so that we can solve some problems in the next video involving free falls. So let's first try to relate velocity and acceleration. So we know that acceleration is equal to change in velocity over change in time. I can actually just solve this equation for velocity. I can rewrite this as acceleration equals VF minus VI over change in time, but that's really just as long as our initial time is 0, we're just talking about how much time has passed, I can call it t. I can multiply t to the other side and I get AT equals VF minus VI. And then I see that my final velocity equals AT plus VI. So what this is saying is that final velocity equals initial velocity plus acceleration times time. And if we want to check units, we would see that, well, acceleration is meters over seconds squared times seconds plus meters over seconds. So seconds cancel here. I'm left with meters over seconds plus meters over seconds. Okay, and then final velocity is in fact measured in meters per second, so that works out nicely. Let's look at an example to see how this works out. So let's look at another example on the next page. Let's say that I am driving, and at time 0, my velocity, my initial velocity is, let's call it 25 meters per second. And let's say that I am accelerating at a constant rate of 5 meters per second squared. What is my final velocity after, let's say, 6 seconds? So one way we can do this is plug into the formula that we derived in the last page. Another way we can look at this is kind of the long way of doing things, is to think about what acceleration is telling us. So let's say that I have, here's time measured in seconds, and here's velocity given in meters per second. So at time 0, my initial velocity is 25 meters per second. Okay, and then I know that my acceleration is 5 meters per second squared. You can think of that as like the slope of the line. Remember that acceleration is the slope of the velocity curve. So we would say that for every 1 second that passes, my velocity increases by 5 meters per second, meaning that after 1 second, my new velocity is 30. After 2 seconds, it's 35. And after 3 seconds, it's 40. And then I could keep going all the way to 6. Or, a little bit more efficient way is use the formula VF equals VI plus AT. Alright, so I'm looking for my final velocity. That's my unknown. I know that VI is 25. I know that my acceleration is 5. And my time is 6. So I get 25 plus 30, which is 55 meters per second. Okay. So I'm able to find final velocity given an initial velocity and acceleration. And it's important to note here that to use this formula, acceleration has to be constant. I can't be accelerating and then decelerating, or accelerating even more at a certain point in that time interval. It has to be constant. So let's now look at a situation where we're going to try and find displacement given velocity. On the next page, let's review that we know that velocity is change in position, so delta x over delta t. Remember that delta x represents displacement, so then we would know that delta x equals delta t, which if we're starting at time 0 is just time from 0. And what I mean by that is t, this is really just t final minus t initial. And if t initial is 0, we're just really talking about the final time. So I'm going to write that as times t v. So velocity times time equals position. And just to double check units, time is measured in seconds, velocity is measured in meters per second. Notice that seconds cancel and I'm left with meters right there, and position or displacement is measured in meters. Okay, so that works out nicely. Now let's look at this graphically. So if I tell you that I'm traveling at 50 miles per hour for an hour, it's pretty intuitive that after an hour I will have gone 50 miles, and after 2 hours I will have traveled 100 miles. So if I graph velocity, so this is a velocity time graph, meaning I have time on the x-axis and velocity on the y-axis, and I'm traveling at a constant velocity. Let's say it's 50 miles per hour, so that's 50. Velocity is measured in miles per hour. And let's say that time is also measured in hours. After, let's say, 2 hours, I will have traveled, you would say your distance, or delta x, is 100. You just do 50 times 2, and that would be measured in miles. But here's an interesting relationship. So if I draw a box from 2 hours, and I look at the area of this box, I see that the area under the curve, under the velocity curve, which is this right here, so the area under the curve is always talked about like under the curve to the x-axis, not, continuing down over here. So just to the x-axis. The area of this box is also 100. I see that, this height is 50, right? This base is 2. Therefore, area equals 100. So in general, area under the curve of a velocity graph is equal to the displacement. So I'm going to write that on the next page. So area under velocity graph equals displacement. This is an interesting relationship. So let's look at another example. Now let's say that I have another velocity curve. So here's time. And we'll say that's in seconds this time. And let's do velocity. We can say that's in meters per second. And let's say that I have initial velocity of 0, so I'm starting at rest. And let's say that I'm walking and I start to pick up speed. Let's say it looks something like that. Okay, so I have constant acceleration in this case. I'm accelerating at a constant rate, so my speed is increasing smoothly. It's not jerky. Okay, and let's say that after 3 seconds, my velocity is 8 meters per second. Now, how far have I traveled? What is my displacement? Well, we already said the area under the velocity graph is displacement. So, I'm really looking at what is the area of this triangle. Okay, well I see that the height of this triangle is 8. And my time, the base of this triangle is 3. So you know the area of a triangle is 1/2 base times height. So it's going to be 1/2 times the base, which is 3, times the height, which is 8. So that gives you 12. And that's measured in meters. So the area under the curve here is 12. And that also means that my displacement, or delta x, in this case is 12 meters. Alright, so we're starting to see maybe a bit of a relationship here. Let's look at another example. So in this next example, let's say that instead of starting at a velocity of 0, again another velocity time graph, so here's time, measured in seconds, and velocity in meters per second. Let's say that I start at an initial velocity of 10, and that I end up speeding up to a final velocity of 20, and it takes me 4 seconds to do this. Okay, so I want to figure out what is my displacement. So again, area under the curve tells us that this area is my displacement. It's just a matter of figuring out what is the area of that shape. So you should notice that this is a trapezoid. These are my bases. Remember, in a trapezoid, one pair of opposite sides are parallel. Okay, area of a trapezoid is given by the average of the bases, so 1/2 base 1 plus base 2 times the height. So my bases are the parallel sides, which is this and this in red. Just highlight that in red. So my base is 10 and 20. Okay, so 1/2 10 plus 20. And my height, I'm going to highlight that in blue, is my time, which is 4. So the area under this curve is 15 times 4, which is 60 meters. That's 60 meters. Let's see if we can extrapolate this to give us a general formula for distance. Okay, so we know that area is equal to distance, so I would say delta x equals 1/2. So B1 really corresponded to this right here, the 10. And what was the 10? That was our initial velocity. So in general terms, I can call that VI plus V2, this right here, corresponded to my final velocity. So I can call that V2, or VF, sorry. Let me erase that. So final velocity. And that's initial velocity. And then the height, this, corresponded to my time. So I'll call that T. So we see by looking at this formula that displacement, when acceleration is constant, is the average of the final and initial velocity times time. And if we look back, that works in all our previous cases. So if I go back to this example, really all I was doing is the average of the initial and the final velocity. But the initial velocity was 0, so just 0 plus 8 gets me 4. Hence the 8 times the 1/2 times time. And in this case, the velocity was constant, So the average velocity would just be 50 plus 50 over 2, which is 50, times time. So in this case, it's just velocity times time. Okay, so in all cases, you can think of displacement, when acceleration is constant, as the average of the initial and the final velocity times time. Okay, now let's kind of look at this formula that we just found, and then the formula we found earlier that related acceleration and velocity to find a formula that relates displacement and acceleration. Okay, so let's try and find a formula that relates position and acceleration. So let's take what we know onto the next page. Okay, we know that delta x equals the average of the velocities, vi plus vf times time. And we know that VF equals VI plus acceleration times time. Okay, so what I can do is I know that VF equals all of this, and I have VF here. So I can sub this in for VF, and I get delta x is equal to 1/2 VI plus VI plus AT, now that's the part that I'm subbing in, times time. Okay, I can simplify this down and I get 1/2 times 2 VI plus AT times T. I can distribute the 1/2 and I get VI plus 1/2 AT all times T. And then I get my final equation, which is delta x equals initial velocity times time plus 1/2 acceleration times time squared. And this is a really important formula that's going to come up quite a bit when we talk about free falls. So there's one final equation that we have to mention that's useful when solving these sorts of problems with like constant acceleration. So that formula is v f squared, final velocity squared, equals initial velocity squared plus 2 times the acceleration times delta x, change in position. We can find this, or we can derive this formula using the last two formulas that we've already found. So VF equals VI plus AT, and delta x equals VI times time plus 1/2 acceleration times t squared. Okay, so we notice that in the formula that we're trying to derive this one, there's no time involved, so I'm going to solve the equation to the left for t. So VF minus VI all over A equals t. And then I can basically plug this in for t here, and then simplify it down. It's a lot of math involved, but you should be able to kind of follow the steps. So delta x equals VI, and I'm plugging in for t, which is this guy. Okay, so I've plugged in for t, and then I'm just going to simplify that down. So I get delta x, oops, distribute in the VI, so VI VF minus VI squared all over A So I distributed in the squared and put the 2 on the bottom. I need to get a common denominator, so I'm going to multiply the first one by 2. So I can have 2a on the bottom. Oops. And I'm going to FOIL out this guy, the one on the right, and then I can cancel off an a. Okay, I see now they have a common denominator of 2a, so I can add the two fractions. I see that these are going to cancel. And I'm left with delta x equals vf squared minus vi squared all over 2a. I can multiply the 2a to the other side. So 2a delta x equals vf squared minus vi squared. Now finally solving for vf squared by moving vi to the other side. Okay, and that's kind of what I was looking to have, this guy right here. So we were able to just derive that third formula using this equation and this equation. If you notice, there's no t in this third equation, so it's useful if you don't know your final time, but you know final initial velocity and acceleration. Okay, so let's kind of wrap this up on the next slide. So our 3 important formulas are Vf equals initial velocity plus acceleration times time. So that gives us final velocity. Change in position is equal to initial velocity times time plus 1/2 acceleration times t squared. And then finally, final velocity squared equals initial velocity squared plus 2 times acceleration times change in position. So those are your 3 important formulas from this lesson. And then an important note here is that to use any of these, acceleration must be constant. Okay? So in closing, let's just talk about some of the relationships we learned. So we've learned that if I take the slope of the position function, so take the slope of this, I get velocity. Okay, then if I take the slope of velocity, I get acceleration. Just going to write it as Excel. Now, if I take the area under the curve of the position function, or of the velocity function, sorry, so area under curve of velocity function, I get my change in position. I get displacement. Okay, so those are some important relationships to think about. And then in the next video, we'll talk about free falls.